cup like this thing?
Well, there's no such thing as a neutral pH indicator.
You needed venting.
None of them
And
really
so
do
then
that.
she goes, or no.
Okay.
So
first
it's
she
gonna be
grabs,
slightly
like,
acidic.
hot
Huh?
like the
Just get a really light color.
Yeah, so I think we might want a slightly acidic one, because what the indicator will show is that all the carbonate's gone then. So at that point, so we want to make sure that at that point, so
I always had
I think
special
we want a
instructions,
slightly
too, on
acidic
those, just like-
indicator.
Yeah.
See, it always stresses me
No,
out.
I'm thinking like how
Because I
acidic of the
like
indicators
thirsty
color
things.
we need to use.
Participant in the conference.
Oh, for different indicators that have different pHs.
Like phenolphthalein is a basic one.
Medium dark.
Yeah. While there's ones that are like only show colors at 12 or only show colors
You
at
want to
2.
try it?
Gotcha.
Try it. It's really
Okay.
strong.
So
I
because carbonate's a base and we're neutralizing with HCl.
How many are
They,
not?
if we start seeing color once the
But I mean, that's
HCl
what it
what
comes with. It's fine.
acid, that means all the carbonate's
Oh my
gone,
gosh.
and that's probably the one we want.
Yep.
Really strong.
So we don't have to do
Starbucks
a
double
number for
shot.
that. for
2
this.
pumps of
No.
coffee, 3 vanilla.
Okay.
She just wanted us to look through the chart and determine what type of indicator we should use.
Yeah, it's
Okay.
good.
Are we
but
supposed to have that written down anywhere or just know it?
I just know what I think, but maybe write it down.
Well,
I hear that I'm in the presence of professional chemists because I see like some keywords like titration, I see, which would probably not. I wouldn't hear that it would be physics or engineering or biology. So, who you are and what are you doing? So it is a physical chemistry class, and we are so impatient to eventually get to prediction of outcomes of measurements of some instruments, like characterizing materials with their spectra and other, I don't know, heat capacity, color, reaction ability to burn. Through activation of reaction barriers, but like, instead of doing this literally and directly, we are bothering ourselves with quantum theory. And the motivation to do it is that properties of atoms and molecules are defined by motion of electrons, who are so energetic, impassioned that they can't stay still, and we need to know how they move. You did nice presentations on fundamental postulates of quantum theory. Like, they are not practical recipes, but they give a framework how to think and how to plan description of properties of these electrons in molecules. Right? So you are certified experts in postulates and in some other things. What else do we have in the class? What is our knowledge baggage? Anything you remember or you think is relevant, of course. What about the future? What can you do with it? Excellent. I see you're doing good in class. So you can predict future of an electron, and you know how to mathematically define past and future. You just write psi wave function at different time in the past, time in the future. This is good. Also, you probably are acquainted with concept of operators, and you even have an intimate acquaintance with one of the operators, with the operator of momentum. What else? Let's just scroll through our memories and try to, or through the notes. Which problem is typically solved in very basic, low level of quantum theory? Some of you was riding with me the elevator and mentioned the right keywords. So
Particle in a box.
this is one of the applications, but more general.
Stationary states?
Yes. So eigenvalues, eigenvectors, eigenfunctions. So it is the most popular problem, and even people who are not big experts in quantum theory speak this language and solve this problem, at least in the course of studies. We cannot avoid it. So there are operators, there are some rules how to construct them, and then there are functions that are eigenstates of these operators. And those things are building blocks to predict future, to describe electrons in the molecules or materials in general. This is a good list. Operators, momentum operator, eigenstates problems, 3 ways to predict future. What else? Important thing. Not most, but the closest one to our goals and motivation. So all this boring theories. So if you know wave function, but our employer wants results of experiment, how do we connect wave function to the outcome of experiment?
A lot of math.
Huh? well, lots of money just hiring the right person, solving all problems. But mechanistically, we already know the recipe. Maybe without too much details. And I'm not yet well enough acquainted with your names, but one of the presentations was on this connection. I remember we had a debate and arguing this one. So if there is we discussed it with everyone. If there are a lot of measurements and our preferred system of interest is not equivalent at each measurement, it can be in one state, another state, superposition, but we want to have a solid number to compare to whatever comes out of measurement. Just think about it. You do not need to answer. I will approach from different side. If a system is an eigenstate, then a measurement will give the eigenvalue of the operator. But if it is not in the eigenstate, it can be something different. And then one uses the concept of expectation value of an operator that corresponds to something that we need for the measurement. So we take operator, quantum operator, and multiply it by wave function from left and right, and then integrating and getting the outcome of experiment. Okay, so it is more or less what we are expected to get. Enough background, and it looks like we are done with the first chapter of basics. So we have bought a car, and we need to ride to a picnic. We just need to find some nice sightseeing to explore. So with these tools, from now on, we will be exploring different applications, different problems, with ramping up the level of complexity on one hand, of course, to torture people, as you probably think about this course. And from other side, to approach to systems complicated enough to be comparable to real life. Because if you start something really practical right now, we will die. We do not have enough muscles, mathematical muscles to process it. Or we don't have enough skills, enough experience to predict difficulties and have the tricks how to bypass them. But if you start with something simple, we will suffer this abstraction from real world, but we will come to the level when we can do useful things. Make sense? Okay. So what are we going to focus on as the simplest possible problem? Brian knows the answer. Brandon knows the answer. I'm just looking who is smiling. Okay. So we are talking about electron. And molecule or atom is electron in the vicinity of something attractive, like nuclei. But suppose we have an electron that travels and is got kept by an ion. Before, like, I don't know, electron departs one molecule, approaches another electron transfer. But in between, especially if the molecules are in vacuum, there is a time interval when it is like standalone electron, not bound to anyone. Bachelor electron. Or we can imagine a fake universe where there are no humans, no planets, no stars, no molecules. There is only one electron. But we want to mathematically rigorously describe what this electron is doing based on our luggage of knowledge, based on the theories that we've got. So it is a task for, I don't know, 5 or meetings. So, before we go to details, I want to make a couple of administrative announcements. Otherwise, we all get too excited into science and forget about that. Remember the email with homework. I apologize, I was planning to print it, but I was not lazy to print it. I just forgot because I was excited and rushing here. But if you all lift hands if you didn't get the email. Okay, meaning that everyone got the homework and everyone is happy about trying to do it. So there is something in common between you and me. We all want you guys to have a maximum possible grades. For you, it's your career. For me, it's record of excellent teacher. I will brag to my colleagues. See how efficient I am. They have all good grades, but I'm expecting a lot of cooperation from your side. So no homework 1. Let's assume everyone got 8. Then everything will go better. So homework 2. I just show this what we do there, this assignments, and then I will make an announcement what will be a program of tonight lab session. Again, no one can twist your arms and bring you to the lab tonight. It is like in the regulations there are only 3 hours, lecture hours. So it is your free will if you come there. So it's highly recommended, but not mandatory. Homework. Some of you may have enough mathematical background to be flexible with Fourier transform. But if you are not, it's not a big deal. It's one of the easiest concepts of the advanced math. So you can look in Google or some textbook. It will be sufficient. It just same. So in application to our course, the Fourier transform is exactly the procedure of finding expansion coefficients. What we finished on our last meeting. So that in order to predict future, we need to process initial condition into the expansion coefficients. Right? So multiplying initial wave functions times eigenstates. In some sense, in some cases, it is literally the definition of Fourier transform. And we want to practice it a little bit to help our lecture material go smooth. So you look what it is. Then there are two types of Fourier transform, or like Fourier Laplace. So one can expand function in basis of oscillatory signs and cosines, like here, any function can be represented as summation of cosines with different frequencies, and one needs to find expansion coefficients. And another form where any function can be represented as summation of exponentials, oscillator exponentials, but idea is the same. So the task is to consider function that is periodic but not harmonic, like a beast, a model of a beast that have half of teeth. One present, one absent, one present, one absent. I don't know, maybe you have some more profile of a castle wall. So periodic but not harmonic. So this function which protrudes infinitely to the left and to the right can be converted into the form of this Fourier transform. So you may want to find the coefficients A and B. Do not feel scared. The homework assumes some investment of time. So do not be surprised if you like look and you do not see and just bringing your answer next second. You need to sit and analyze but it is not deadly thing. If you invest this amount of time, you'll get the right answer, and I will be happy to chat on this. So, second one, if you will listen and take notes of our today's meeting, you will conclude by rest. You just copy paste from what you will do. And the third one is another form of Fourier transform. So you take this function, multiply it, and integrate, and just report what you get. Here's X. Right now it is blocked by this sound detector. It works. This green stuff pop-ups when you shoot or make some noise. Okay. You got general idea what is in core. And let's bring it to the class in a different one. We have the whole weekend. Some level of being scared will be present in your souls. And it is a healthy. I anticipate it. Main reason of you being scared of mathematical tasks is to move you towards computational modeling, which is 100 times easier. Right? So some problems that are hard to solve by pen and paper can be made in a few minutes just by writing 2 lines code or whatever, or using some software as a big calculator to solve quantum problems. So we will have another chapter, segment of our course with very basic, very primitive modeling using so-called MATLAB software. And it is fine if you never saw it and never used it. So most of our evenings on Wednesdays will be related of MATLAB for quantum theory or for physical chemistry. Again, you can decline to come. You will survive, but it will be harder. So if you come and just half sleepy listening, it will make your life easier. At least from my point of view. Any questions about administrative side of the course? Objections? Yes?
I guess I am just curious for like that recitation class or that one later tonight. When we start working with things like MATLAB, will we be meeting in some kind of like computer lab where we'll all be working on the same thing?
I think it's in the big lab downstairs.
I think it is 122.
Okay, perfect. I remember seeing QBB, but honestly, I just thought it was
Downstairs.
Okay.
I can be wrong with number. It can be 132. I think it is 122. But if you just walk in the corridor and hear laughter and loud talking, you recognize the place.
Okay,
132.
132.
Huh?
132.
Okay. Yeah.
Thanks.
So I was going to give you money, but I forgot to print it, like fake money. Like here in this country, the currency unit is dollars. What is the currency unit in Europe?
Europe, euros.
Euros. When did they introduce it?
Depends on which country you're talking about.
Germany.
Germany, that was earlier on.
2002? 7? Maybe. I don't care. I left it in 2000. So before this European Union and common currency for the whole Europe, they used to have national currency. And the currency in Germany was German marks, Deutsche marks. So whose faces are shown on American currency? Presents. Guess whose faces are shown on this obsolete German currency? Well, different people, but I'm impressed by 10 marks note. So,
Scouts, isn't it?
yes. So he's a scientist, mathematician, not a president. So this, I should bring more of this money and distribute. This is a very useful and important handout for our class. You can, what are your class notes? My class notes are money. I do not bring anything else. And in these circumstances, it will be very. So if you focus your glance in this area, it shows a function that is introduced by the scientist. And we will be dealing with this function for 4 minutes. So we can bring money as a class didactic healthy material for a week or even longer. So it's exponential to the power minus second power of argument, e to the power minus x squared with some garbage constants. Well, not garbage, but I'm lazy to memorize. It's just zoom in. So here is our plan, and we will not complete it today. It's just beginning, but we go through several steps. So no one was objecting, maybe because even if you do not like it, maybe just because you're so polite, but no one was objecting to study electron in vacuum. And you are growing hope of world science, meaning you develop your scientific type of thinking. And before we start doing boring math or exciting experiments, we may use our common sense or previous scientific experience and develop hypothetical statements, like what are we going to get? Like math is a servant of a chemist and physicist. It's not a standalone thing. It has no value. It's just a servant to us. So which order we want to give to ourselves or to a mathematician whom we hire? Like on one hand. On another, if all our plans will be completed, if we travel to a picnic in a desired direction, which sightseeing are we going to see? So which properties of electron in a vacuum we may anticipate and then prove right or wrong? So anything you think anything you were thinking starting from kindergarten about free electron in a vacuum? Just share your vision. Before we start rigorous treatment, anything is okay.
I don't know, this is probably the wrong path, but I guess I may be object to going down that path just because there'd be no kind of movement or anything that we could like get from the electron. There's no forces if it's just the electron, so there should be no movement along with it.
Good. So, no. What did Newton told you?
There needs to be a force for some
Yes,
kind of
but
movement to actually occur.
before he started talking about forces, what's his first law?
An object in motion tends to stay in motion.
Yes. So you're right in the aspect that if we prepare electron to stay still, then no one will make it to move because no one else is present in this universe. But if you launch it to move, it will continue to move. So we may rediscover this simple thing. And x of t, if we decide for its average position, will be position at time 0 plus velocity, which is momentum over mass, times delta t. Right? It is what you wanted to suggest.
Mm-hmm.
What else? What else do we expect? Let's recall our discussions about probability, interpretation of the function, about the nature that electrons, even with very small energy, it likes to move. And it likes to occupy more space than it is allowed. Aggressive expansion. So suppose we did all our scientific skills and apparatus to squeeze electron and place it into a very small amount of space, like a cube or maybe a sphere. But then we remove any constraints and let it sit. What will you expect? Will it shrink or expand or stay unchanged? Just intuitively.
I would think unchanged.
Unchanged. Any other opinions? With arguments or any without arguments? Well, based on the question, you can guess that there are some other opinions. So shrink or expand?
I guess expansion.
Why?
I guess because if you constrain it within a small area and then you open up that box to a lot larger area, then it has room to expand due to disability.
This is a very good scientific hypothesis. So we will set up our whatever 4 meetings exercise as to prove right or wrong 2 hypotheses. First, that it moves according to initial velocity, and second, that if you have distribution of probability for electron to reside at a specific space, the area taken by this distribution will expand. Maybe we will find otherwise, but it is at least something we can anticipate, and then we sharpen our efforts to focus on these 2 aspects. And then it will be less philosophical, more specific, more concrete. Expanding electron. Yes or no? How much does it expand? And here is what we already discussed. We know concepts of some plane wave, Schrödinger equation, eigenfunctions. ways to predict future by expansion of initial conditions, right? One day we can do a recalling session and bring up these equations, but for you, you can just flip over your notes if you are taking them and see this equation. So moving linearly, expanding, taking more and more space, probably. And we may want to play true scientists or be a true scientist. So expand is too vague. We can tell like size of electron or maybe the half heights, widths, same like one does for spectrum, or threshold. If the probability is bigger than 1%, we discuss it, we debate it as radius of our squeezed electron. So we can assign this letter sigma as a size of a space occupied by electron. And then our science can be targeted to find dependence on this as function of time. Okay. It is very good formulation of a problem. It is something that our skills would allow us to do. There will be a little effort, but it is a good problem. I promise we will solve it. So, how are we going to start? And by the way, here's the answer. It's you can look at it so that it will be a proof that there is an answer. But right now, it doesn't tell us much, and we still, our main goal is not to address this rather primitive problem, but develop methodology, protocol, how to get to this answer. So it's not a big deal here. It will be position minus initial position minus momentum or mass times t. Under this, here will be a square Gaussian function, and in the denominator, the width parameter will grow quadratic. Someone is wait half an hour. I did this when I was undergraduate. So, how do we get to this answer? Guess what we are going to do. So we were recalling our arsenal of skills, not just to entertain ourselves or torture ourselves. It was intentional. So we need to predict future, right? We need to go from past to the future. Our past is squeezed electron. Our future is unknown electron. So we need the initial condition, which will be wave function x and t equals 0. And by the way, another approximation. Let's consider that our universe is one dimension, because 3 dimensions is too much for us. Let's do baby steps. And we need to go to the future, which will be psi of x over t bigger than 0. For interpretations later, after we get this wave function, we want to take absolute value square. But first, we need to go from past to the future. So, in order to go from past to the future, what do we do? What is our protocol? You were contributing enough. I will speak. Yeah. So our future is a summation of all eigenfunctions. By the way, eigenfunctions. We'll discuss on the next slide.
A wave function?
Huh?
A wave function?
No. Wave function, which is the same as eigenfunction of what? Of which operator?
Okay.
You cannot be wrong telling eigenfunction of Hamiltonian. You can, in 99.9% you will be correct. But which Hamiltonian? So you need a Hamiltonian of electron in vacuum. Then we need energies of electron in vacuum. And then some expansion coefficients. So basically we need to, which will depend on the past, on initial condition. I think the C is okay. So basically we need to fill these three components and then perform this summation. And then we will get the answer. And everyone, especially me, will become happy. This is the plan. How are we doing this time? 5, 10, 15.
It's 11:35 right now.
Okay, so, oh, that's generous. We have about 15 minutes. We can progress substantially on this plan, but this is something you may put down in your records. It will take us more than today's meeting to go through this plan. So fill each component of this expression and perform summation. And then we will get answer which will prove right or wrong the hypothesis of expanding electron. Okay? Wave functions of what? Which functions and of which operator? We do not behave rigorously as people do in math. We do little experiments. And we do not know much functions that we are familiar with. Let's repeat a simple mathematical experiment and then do a wow moment. And, oh, it's an answer for this question. So we do have two pieces of knowledge in our baggage. First, that kinetic energy is equal to what? Energy of motion.
And v squared.
And if we do not have velocity but have momentum, v equals p divided by m, right? Because p is equal to mv. So how do we convert it? If you replace v by p over m.
V squared over 2m.
Excellent. If there are no ions, if the special electron is free, it has only kinetic energy, right? There are no potential ions. On the other hand, we are approaching tricks of quantum theory, so we do not write just p like simple. We always want to add hat on top. So what is the momentum operator? It's the only thing that you need to memorize. The rest we will derive.
Negative I r derivative 1 spatial coordinates.
So how do we form p squared over 2m? It's just having this operator and take it squared. So I times I will be minus 1. Minus 1 times minus 1 will be 1. So just plus. r squared 2m d2 d squared. So we set up first Hamiltonian in your life. You derive a Hamiltonian of free electron in the vacuum. Now, for our prescription protocol, we need to know eigenfunctions and eigenenergies of this Hamiltonian. We need to place something here, there, and there. Functions, phase activations due to eigenenergies, and expansion coefficient. So, to get these energies and functions, we need to solve stationary Schrödinger equation. And in whatever follows in the course, we will solve such equations. But now we will just guess the solution and obtain a positive surprise that a guess solution will match this equation, just to save time and because everything is set up in a simple way. H equals minus d plus 2 d squared. Why don't we try our favorite function and check whether it will help us to solve this equation? So we can call it math experiment. Try e to the power minus I-ax. Instead of k, we can use p like h bar to dimensions. So h prime dx minus I. So we keep the constant in first derivative, the last derivative unchanged, and take this derivative. What are we getting? The minus all factors come up front, and the function stays unchanged. E to the power minus I ax. Right? Now this factor can migrate to the front, and taking derivative once again. So we get this factor minus I once again, and the function stays unchanged. Minus I, right? Take the first derivative, the second derivative. Then we multiply this factor. Minus times minus to the plus, and I times I will be should be. I was so excited that I already made an error.
Should there also be a coefficient in front of the exponential?
Yes, but we will die if we will process the
coefficient.
There should be normalization. So it's minus, and then you have one more minus because of multiplication of imaginary units. Then h bar squared all 2m p squared e to the power minus I ax. So here these two minuses compensate, and we will get h bar squared k squared m times the function we started from. So what did we do? What did we came through? We take a guess function and we checked whether it will be a solution of the eigenvalue problem. So we applied Hamiltonian to this function and realized, what a surprise, the function hasn't been changed. Through application of the differential operator, we obtained some factor up front which we can interpret as energy. But the function didn't change. It was oscillator exponential and it is oscillator exponential. Good. And the p times h is momentum. So this expression here, h bar squared k squared over 2m, is actually p squared over 2m. So coincides with what we may want to have. But here the p is not an operator, but the eigenvalue of the operator. It's number, not an operator. So we built Hamiltonian. We didn't set up initial condition that we should do. And our output in our exercise will be to find the function and then construct probability distribution. So we already have solution of stationary state eigenvalue problem in the yes. So for our protocol, we already have something to fill inside the red box and green box. Okay? So instead of this phi over k, we will put in e minus I ax, and instead of e sub k, we will put so we are 66% done. Now we need to find expansion coefficients. So in order to find expansion coefficients, we need to set up initial condition. So here is the moment of creativity. Instead of doing boring math, we can design initial condition, anything we like. Anything I like. You did agree that in our scientific approach, we want to start with squeezed electron. So why don't you try to describe initial function for the squeezed electron according to Dr. Gauss. So let's electron sit in the vicinity of some initial position. Then it has some width. So in our one-dimensional space, we have a bigger probability to find it near x, sub-zero, and less probability apart from it. Objections? Okay. So let's call it x, comma 0, or time equals 0. And now we need to plug this initial condition into our recipe of obtaining expansion coefficients, C sub t. We do know the functions, which are exponentials. We do know our initial condition. And we know how to integrate. So if we perform this operation, we will have C sub k that we can plug into our recipe. So this question is a part of the homework. When we meet in lecture class on Friday, I will assume that you know the answer. I will just use the answer and not without showing you the path how to do it. Today we are meeting at which time? 5 downstairs this building. And where should I go?
132.
132, yes. I have the nicest possible slide that everyone will enjoy. So, meeting is dismissed. Looking forward to see you today at 5. We'll stay here to answer any questions that you have.
Yeah.
It's so simple. I trust that everyone.
What? Reference to the textbook.